From the outset, building a giant oil tanker begins as an exercise in logistics and heavy civil coordination. Before a single plate is welded, shipyards must prepare enormous keys and block assembly areas capable of handling modules that weigh hundreds of tons. Engineers survey the site, marking precise keel lines and grid references to ensure the ship's backbone will align to millimeter tolerances. Quay reinforcement follows, piles are driven, bearing slabs poured, and gantries positioned to deliver the lifting capacity needed for later lifts. Meanwhile, the supply chain hums with activity as steel plates, prefabricated sections, and piping bundles arrive and are staged in yards stretching for city blocks. Specialized teams set up block assembly jigs, massive fixtures that hold preformed hull panels in perfect geometry during tack welding. In parallel, measurement crews deploy laser trackers and geodetic instruments to monitor foundation settlement and alignment. The keel preparation phase includes not only physical groundwork, but also logistical choreography, sequencing deliveries, verifying certifications of steel grades, and preparing heavy lift cranes and barges. Here, safety routines and quality control protocols are embedded in every action, because the alignment and stability established at this stage become the baseline for the entire vessel. When the keel line is certified, the yard is ready to transform stacks of steel into a single, fluid hull that will carry millions of barrels of cargo across oceans. The tanker's hull begins to take form inside vast fabrication halls where steel plates are cut, shaped, and welded into modular blocks. Automated CNC plasma and laser cutters slice plates to precise nest patterns, minimizing waste and ensuring each section fits the assembly jigs. Large rollers curve plates into the longitudinal shapes required for the double bottom and side shells. Skilled teams then position these panels within robotic and manual welding cells where tack welds hold geometry while full penetration welds create continuous structural seams. Non-destructive testing, ultrasonic scans and radiography, is performed on critical welds to detect inclusions or voids. Fabrication focuses not just on flat sections but on integrated stringers, stiffeners, and longitudinal web frames that give the hull its longitudinal strength. Pre-assembly of tank top and inner bottom panels also occurs here, including the insertion of corrosion-resistant coatings in cargo tank areas. Block sizes are engineered to balance transportability and lift limits. Each module is a small, self-contained structural volume with pre-installed pipelines and cable trays where feasible. Quality control teams log material traceability, welding procedure qualifications, and dimensional reports. The output of this phase is a sequence of giant blocks, each a building block of the eventual hull, ready to be transported to the quayside for mating and hull assembly. Keel laying transforms modular blocks into the continuous backbone of a tanker. Blocks are moved from fabrication yards by SPMTs or barges and positioned under towering gantry cranes. Using alignment keys and massive butt straps, shipwrights bring edges into contact and perform initial tack welds to establish continuous structural continuity. Surveyors constantly check longitudinal and vertical alignment with total stations and laser reference systems. Tolerances are minute when the final hull must meet hydrodynamic and loading predictions. As blocks are joined, longitudinal splice welding stitches them into longer segments, and internal access platforms are installed so fitters can continue outfitting from inside. Structural fairing begins immediately. Grinders, plate bevelers, and finish welders smooth transitions so the hull will yield predictable flow when launched. Reinforcements such as collision bulkheads, void spaces, and double hull partitions are integrated during assembly to meet regulatory and safety codes. Temporary supports and jigs keep the hull true during welding. Heat input management plans prevent distortion across long seams. This phase represents the literal assembly of the ship's bones. Once several megablocks are fused, the hull's geometry is fixed, and the project accelerates toward final hull completion and pre-launch treatments. After the hull's blocks are integrated, the shipyard undertakes the demanding task of continuous hull welding and surface preparation. Welders perform long, continuous seams that require strict control of heat input and sequential welding patterns to avoid warping. Grinding and fairing crews follow to remove excess material and prepare surfaces for corrosion protection. Blast cleaning strips mill scale and prepares base metal for primer and epoxy coatings engineered for seawater and crude exposure. Multiple coating layers are applied in climate-controlled booths to ensure adhesion and uniform thickness. Concurrently, structural surveys and ultrasonic thickness measurements verify plate integrity after welding. Preparations for launch involve removal of temporary scaffolding, final fitment of keel supports, and arrangement of skidding or float-off systems. If the vessel is to be launched via drydock flooding or slipway slide, engineering teams carefully plan hydrostatic loads and buoyancy. Condition reports capture lift points and center of gravity data to guarantee a safe launch operation. This phase transitions the tanker from agglomerated steel pieces into a weatherproof, sea-capable shell, ready to receive the complex outfitting that will turn a hull into a working oil carrier. Outfitting is where the tanker's mission is built into its structure. In the vast interior, fitters erect cargo tank subdivisions, cofferdams, and trunking systems. Cargo piping, the manifold network that moves oil between tanks, pumps, and shore connections, is laid out and welded with precision. Pumps and cargo handling equipment are installed on strong points in pump rooms below deck, with flexible couplings, suction lines, and discharge manifolds carefully aligned. Inert gas systems, essential for reducing explosion risk, are fitted with blowers, scrubbers, and piping to maintain safe atmospheres inside cargo tanks. Valve trains, sampling lines, and leak detection sensors are integrated across tank boundaries. Pressure and hydrostatic testing follows. Tanks are filled or pressurized to verify structural integrity and weld tightness. Cathodic protection systems and tank coatings are applied to prevent corrosion from aggressive crude blends. Parallel to cargo systems, structural penetrations for piping and cable routes are welded and reinforced with proper collars and seals to maintain the hull's watertight integrity. This outfitting phase is highly integration-centric. Mechanical, electrical, and safety systems must coexist within compact spaces and meet stringent classification society standards before the ship can proceed to trials. Propulsion installation turns stored energy into thrust. The main diesel or dual-fuel engine, often one of the largest single rotating machines in the ship, is craned into its bed and aligned to the shaft train with micrometer precision. Stern tube bearings, stern tubes, and the propeller shaft are installed and dynamically balanced to minimize vibration. The propeller, sometimes a 5- or 6-blade high-efficiency unit, is fitted and pitch-calibrated. Auxiliary systems, generators, compressors, and boilers, are mounted in the engine room, along with fuel handling and purifier systems to keep fuel stable for large bunker capacities. Switchgear, busbars, and control panels are wired into the vessel's distributed power system and tested under simulated loads. Accommodation blocks are completed in parallel. HVAC, plumbing, sleep quarters, galley and bridge electronics are installed and commissioned. Fire suppression systems, bilge and ballast control panels, and maneuvering thrusters are tested to ensure redundancy and safety. This phase readies the ship's mechanical heart and living spaces for the intensive trials that will follow. Sea trials are the final proving grounds where design meets reality. With the vessel afloat, classification society surveyors, flag state inspectors and owner representatives execute a comprehensive test program. Engine trials validate continuous power and fuel consumption profiles at various loads. Shaft trials and full power runs test vibration, cavitation, and propulsive efficiency. Maneuvering tests, turning circles, crash stops, and low-speed thruster operations, confirm handling under realistic conditions. Cargo system trials verify loading and discharge sequences, stripping, inert gas functionality and leak detection. Safety drills simulate emergency scenarios, testing firefighting systems, evacuation procedures and emergency power resilience. Data collected during trials is scrutinized. Vibration spectra, fuel curves, structural strains and engine thermals are compared to model predictions. Any deficiency triggers corrective action and reinspection. Once the vessel satisfies performance, regulatory and contractual criteria, the delivery ceremony formalizes the transfer to the owner. Flags are raised, certificates issued, and the tanker departs to begin commercial voyages, an outcome of thousands of coordinated steps that turned raw steel into an ocean-going oil carrier.